Googol. A googol is 10 to the 100th power. Written down, this is a 1 followed by 100 zeros. It is also known as 10 duotrigentillion. The word Googol was originally invented by Milton Sirota in 1920, when he was only 9 years old, possibly drawing inspiration from a comic character named Barney Googol. Sirota was the nephew of the American mathematician Edward Kasner, who brought the number to public attention in Mathematics and the Imagination, a book he published in 1940. There is nothing mathematically special about this number, but it can be used in comparisons with other very large numbers. For example, it is much greater than the number of protons in the observable universe, known as the Eddington number, currently estimated to be around 10 to the 80th power. If you had 100,000 copies of the observable universe and packed them all completely full of grains of sand, the number of grains would be about a googol. It is also roughly the number of years a galaxy-massed black hole would take to decay from Hawking radiation. Shannon number. The Shannon number, 10 to the 120th power, is a large number that arose in the early days of computer chess. The calculation is simple. In chess, a move consists of each player taking their turn once consecutively. Shannon estimated that there were about 10 to the third possibilities per move, and that a game consisted of each player making 40 moves. Alternatively, this is 80 plies, where a ply is one player making one move. Thus, the total number of possibilities overall is about 10 cubed to the 40th power, or 10 to the 120th power. This estimate was meant as a lower bound, so all of the estimates are conservative. The point of the Shannon number was to demonstrate that brute force algorithms would be highly impractical for solving chess. This number was given in Shannon's 1950 paper, Programming a Computer for Playing Chess, the first ever paper written about computer chess. The actual number of possible games after n moves can be calculated for small enough n. White has 20 possible starting moves, so the number of possible games after White's first move is 20. Then, Black has 20 possible starting moves after that, and that 20 times White's 20 makes for 400. The calculation gets more complicated from here, as the number of possible moves begins to depend on how the game was previously played. But we get very large numbers very fast. After only Black's fifth move, there are about 69 trillion possible games. Since most of these games would be total nonsense, some have also asked what the number of reasonable chess games would be. The calculation is very similar to that of the Shannon number, but instead it is assumed that each player has about 3 reasonable moves per ply. Assuming an 80-ply game, this yields 3 to the 80th sensible chess games, about 1.48 times 10 to the 38th power, or 148 undecillion. Skewes' numbers. To understand Skewes' numbers, we must start with 2 functions, the prime counting function and the logarithmic integral function. The prime counting function, denoted by pi, no, not the number, takes in a real number and tells you how many prime numbers are less than or equal to that number. For instance, pi of 7 is 4, since there are 4 prime numbers less than or equal to 7, 2, 3, 5, and 7 itself. It is an important function in the field of number theory, which studies integers and arithmetic functions. The logarithmic integral function is a function defined by an integral. Li of x equals the integral of z to x of 1 over the natural log of t dt. The integrand has no elementary antiderivative, so this expression can't be simplified. The prime number theorem tells us that this function is a very good approximation for the prime counting function. However, for relatively small natural numbers x, Li of x is always slightly greater than pi x. It may appear that this would go on forever and ever, but this is not actually true. Pi x does eventually outpace Lix for natural numbers x. However, the value of x required to do so is absolutely massive. The first person to take a serious consideration to this scenario was British mathematician John Eddington Littlewood. In a 1914 paper, he proved that pi of x alternates between being less than and greater than Li of x infinitely many times, contrary to all available numerical data at the time. His paper did not provide any explicit statements on the size of this number, however. The first person to make progress in this area was South African mathematician Stanley Skewes. His proof involved the Riemann hypothesis, which conjectures that the Riemann zeta function's zeros exist only at the negative even integers and complex numbers with real part 1/2. Skewes proved that if the Riemann hypothesis is true, then a number x for which pi x is no less than Li of x must be less than e to the power of e to the power of e to the power of 79. Here, e is Euler's number, the base of natural logarithms, about 2.718. This number is in the size range of 10 to the power of 10 to the power of 10 to the power of 34. If this number were written out, 34 would be the number of zeros in the number of zeros in the number of zeros after the digit 1. Graham's number. Graham's number is a number originating from a problem about graphs in Ramsey theory, specifically about coloring a complete graph of the vertices of a hypercube in n-dimensional space. Graham's number can be described as follows. Exponentiation is repeated multiplication. For instance, 3 cubed is 3 times 3 times 3. Using Knuth's up arrow notation, exponentiation can be denoted by an up arrow. Similarly, tetration is repeated exponentiation, denoted by 2 up arrows. 3 double arrow 3 equals 3 cubed cubed. Exponents are evaluated top to bottom, so this expression is evaluated as follows. Pentation, using 3 arrows, is repeated tetration. 3 triple arrow 3 is 3 double arrow, quantity 3 double arrow 3. Adding another arrow simply iterates the previous operation in the sequence. Now, 3 double arrow 3 is about 7.6 trillion, as previously discussed. So, we get 3 double arrow 7.6 trillion, which corresponds to a tower of exponents, or power tower, containing 7.6 trillion threes. Already, this number is too large for any physical analogy with the observable universe. Its digits cannot be fully written down in the observable universe, even for digits the size of a Planck volume. The digits in its number of digits also cannot be written down, and this continues for a number of times much greater than the number of Planck volumes in the observable universe. Now, consider the number 3 quadruple arrow 3, which is even larger than 3 triple arrow 3. Let's define a sequence of numbers G1, G2, and so on, where 3 quadruple arrow 3 will be G1. The number G1 represents the number of arrows between the 3's in the next element, G2, represented like this. This, in turn, represents the number of arrows between the 3's in the next element, G3. This is done again and again until finally we reach the number G64. This is Graham's number, named after American mathematician Ronald Graham. Tree of 3. In graph theory, a graph consists of vertices that are connected to each other by edges. Graphs can be directed, meaning each edge has a sense of going in a particular direction, where each edge can be thought of as an arrow pointing in one direction. Graphs can also be undirected, meaning direction doesn't matter. A path is a sequence of edges, possibly just a single edge, leading from one vertex of the graph to another. A directed path is a path where every edge is directed in the same direction. A tree is a graph where every pair of 2 vertices is connected by exactly one path. A forest is a graph consisting of a collection of trees that aren't connected to each other. A rooted tree is a single tree with a single vertex designated as the root, called R. There is also the concept of ancestry. If the path from R to some vertex W passes through some other vertex V, then V is an ancestor of W. A common ancestor is an ancestor shared by two vertices. One tree, T1, is contained in another tree, T2, if the vertices of T1 can be matched with same colored vertices in the second tree, T2, and the nearest common ancestor of each vertex is preserved. Now, imagine playing a game with three colors of nodes: black, green, and red. Using these nodes, you have to construct a forest of trees, where each tree is a graph consisting of nodes connected by edges. The first tree must have one node. The second tree must have anywhere from 1 to 2 nodes. The third tree must have 1 to 3 nodes, and so on. And you can't make a tree containing a previous tree. The largest number of trees you can possibly make is tree of 3. In general, tree of n asks how many trees you can make with n vertex colors. As it happens, tree of 3 is an absolutely massive number. To compare with our earlier G sequence, an approximation for the lower bound on tree of 3 would be written like this. Rayo's number. Rayo's number, named after Mexican philosophy professor Agustin Rayo, arose in a 2007 MIT Big Number Duel. It relates to the topic of first-order set theory, which is the commonly used standard when it comes to axiomatic formalization of math. In any given language of first-order set theory, a number may be named by a certain expression. Let's say we limit ourselves to using, at most, a Googol symbols from such a language, where any number expressible under this restriction is called Rayo nameable. There's no special significance to a Googol. It's just what Rayo felt like choosing. Now, Rayo's number is the smallest number that is bigger than any finite Rayo nameable number. That's the basic explanation, though the formal definition of Rayo's number involves a formula using second-order logic, which is an extension of first-order logic. Rayo's number has been claimed to be the largest named number, though what numbers exactly qualify for that title is debatable. In any case, the number was good enough for Rayo, who won the big number duel decisively.